Hey guys, hope everybody's having a good weekend. I know you all are really busy with work and family and trying to keep up with the class here and trying to give you some things to help you out here somewhat. This last 3 weeks of class is really loaded heavy, so you guys are going to have to work. If you want to be successful at the class, you're going to have to study, and I'm going to encourage everybody to watch this video as well. I'm going to give you some stuff to help you here. I want to first look at the calendar, and you notice that it's pretty busy here. So starting this week, we're looking at combination circuits in both 1 and 2, and you need to finish this quiz and try to do that before class time if you possibly can. So work hard on that. And then the next week we jump right into transformers, and I'm going to show you how to calculate the ratios on the transformers and things like that, and we'll try to give you some understanding of transformers and how they work. And then the final week here, you'll be doing the lab. I wanted to try to do the lab on the week before, but there's just not enough time, so we're going to do the final lab, and you'll have to take the SOCA certification exam that week. So when you get to class on your last day, first thing you'll do is take the SOCA certification exam, and then we'll do the final lab. Okay, the written final exam will be available from the 23rd through the 31st, so make sure you get that done. It's 100 questions, and it's not an easy test. I'll just tell you right up front. I think I've already told you this, so don't mean to scare you off, but I just want you to be prepared for it. So if you come back up here to today, the 11th, you see here that I have the final exam practice in Module 15 available for you. So I encourage you to take that any number of times. It's 100 questions, and it's the same questions that you'll have on the test. This will not only prepare you to take our final exam, but it will also help you take the SOCA certification exam. So again, the SOCA, you are graded on the fact that you take the exam, but your exam score will not be reflected in your final grade in this class. So it's a participation thing, and the school is paying for you to take the exam. There is a fee for that, so they want everybody that's in the class to take the exam. So we have to put some weight to that without actually counting that to the score. So when you take it, you get a silver certification, and then we're getting set up so you can get a gold certification in it, which means that you can do the hands-on component of the class. I don't think we're quite ready to do that, but we should be in the very, very near future with that. So let's go on over to the class and look where the exams are at to make sure everybody knows. So if we go down to Module 15, you'll see the practice exam there. I still got to go way down here, don't I? Module 15. So you have the final exam practice quiz, and like I said, it says 100 points. I'm not sure. And there's no time limit on it, and you're allowed multiple attempts. And there are 100 questions on it. So we can, since it's a practice, we can pop in there and look at it. So if you look at it, you're going to have some questions like this about schematic symbols and things like that. Now you use your notes. You got notes on all this, and just make sure that you use your notes and take your time on it. Since there's no time limit, take your time, but allow yourself enough time to complete this. So we'll go back to the modules here and then back one more. And if you look in module 16, then you'll find the final exam and the final lab. And we'll pop that up and look at it here. It's no big secret, but so you got to wire a circuit with a light on it and calculate the things, and it's pretty easy. Okay, well, pretty much the same as the midterm, except now you're using light bulbs instead of resistors. So you got to do a series circuit, 2 series circuits, and a parallel circuit. So that's that. Just to give you a heads up on what's going on here. Okay. And now let's go back. So that's a heads up. Now I'm telling you there's a lot of work to do, and we're going to be covering 2 very big topics in just a week to allow for each of them. So I wish we had 2 weeks for each of them, but we don't. So it is what it is, and we'll just make the best of it here. Okay, now it's on to our study topic for this week, combination circuits or series parallel. And if you look at the labs for this week, they're all just a whole bunch of calculations. So you got to we'll do a lot of those together in class, so we make sure everybody understands how they work. There's some more complicated circuits than what I'm going to show you here, but I'm just showing you a basic series parallel circuit so you can see how the steps work. And I've got a 5-step process to do these calculations. And if you do all the steps in order and complete each one correctly, then you'll get the answers right. So let's go ahead and so here's a basic series parallel circuit. We have 12 volts applied to a series resistor R1. That's 100 ohms, and then a branch with 3 resistors, all 100 ohms, R2, R3, and R4. So a real basic series parallel circuit. So let's analyze this circuit. Step 1, we got to determine the component relationships. Okay. Step 2, we'll calculate the total resistance. Step 3, we'll calculate the total current. Step 4, we'll determine the voltage drops. And then step 5, we'll calculate the individual branch currents. Okay, so here's a basic series parallel circuit, and the way that we determine the relationships of the components in the circuit is to very simply trace the current flow. And since I'm an electron flow guy, we start with negative side of the power supply and come out and then go around the circuit back to the positive. So total current will flow in that wire, and then when it gets to the branch, then it's going to branch off to each resistor. Depending on the size of that resistor will depend on how much current will flow through each leg of the branch. So we have, and since these resistors are all equal, we're going to have an equal amount of current flowing through each resistor, and then the individual branch currents combine back to the total current again and go back to the positive side of the power supply. So we can deduce from this analysis that R1 is in series, R1 here is in series with the parallel branch R2, R3, and R4. Okay, and that's very important for us to continue now with our analysis. So we're going to calculate the total resistance, and we're going to use our reciprocal formula to calculate the parallel resistance. We're using the top one here. We don't have two resistors there, so we can't use that one. But we can use R1 plus R2 plus R3 for this case. So go to the most complicated part of the circuit and find the resistance. So this parallel branch is the most complicated part of the circuit. Again, when you see some other circuits, there's going to be some with more complicated parts, but right now, for this circuit, this is the most complicated part. So now we're going to calculate the total resistance using our reciprocal formula. And so remember how to do that. If we have, I'm going to make sure I'm cleared out here because that always gets me in trouble. So we have 100 reciprocal plus 100 reciprocal plus 100 reciprocal equals, and then we got to hit the reciprocal key one more time, 33.333 continuous. So that is our resistance of our parallel branch. So the parallel resistance, we can drop off a bunch of those threes and just say, and really I would, if I was doing this just for a general quick calculation, I'd just say it's 33 ohms. But our test final exam's a little bit picky about if it tells you the tenths or the hundredths. Make sure that you include those in your answer. And again, I'll go back and review your test, and if I see that you, like if it was 33.333 ohms for this question and you wrote down 33, I would count that right. I'm not that picky with this, okay? So then we add the parallel resistance to the series resistor, R1, and because we said that R1 is in series with this branch. So R1 is 100 ohms added to 33.33 ohms, and we get a total resistance of 133.33 ohms. Pretty simple stuff right there at that point. Okay, so now let's look at that again. There we have 33.33 ohms there. If we put our ohm meter across there, took the power off, remember, and put our ohm meter across from the top of that branch to the bottom of it, we would measure 33 ohms or something real close to that. And then again, if we measured across there, we'd measure 100 ohms. If we measured across the whole circuit, we'd have 133.33 ohms. Okay, so we've established that fact. Now let's look at how to calculate total current. So what two things do we know about the circuit that will allow us to calculate total current? Clear this out. We know total resistance, which is 133.33 ohms, and we know total voltage. So remember Ohm's law, voltage divided by resistance equals current. So 12 divided by 133.33 equals 0.090. That's close enough for right now. So using Ohm's law, we have 12 volts divided by 133.33 ohms, and our total current is 0.090 or 90 milliamps. So we have 90 milliamps, and now we're going to calculate the voltage drops, and we have to calculate the series voltage drops first. Remember, we have 12 volts to spend on this circuit. We're going to spend so much to get through each resistance. So we're going to spend so much to push the electrons through the 100 ohm resistor, and then we're going to spend so much to push it through the 33 ohms here. Remember, it's not 100 ohms here, it's 33. So we can use logic to determine that it's going to take a whole lot more voltage to push the electrons through 100 ohms than it is 33 ohms. So it's going to be about 3 times greater a value here at R1. And we'll prove that mathematically now. So again, we use our friend Ohm's law, and we have 90 milliamps. And so we're going to bring up our calculator here again, and we say we have 90 milliamps going through a 100 ohm resistor. So remember Ohm's law here, I times R equals E, or voltage. So 0.09 times 100 equals 9 volts. Okay. So we have, if we measure with our voltmeter across from side to side on this resistor, we would read 9 volts or close to it. Okay? And now let's calculate the voltage drop of the parallel branch, still using Ohm's law. And we have 90 milliamps going into 33.33 ohms. So that comes out, let's do it on the calculator here again. And you're going to see that it won't come out quite to that. So 0.09 times 33.33 equals 2.9997, which is approximately 3 volts, okay? So we could also apply Kirchhoff's law to that, his voltage law, which, my paraphrase, the sum of all voltages equals the source voltage. He says it backwards as far as I'm concerned. He says if you add up the algebraic sum of all the voltages around a closed loop equals the voltage going into that loop. So same thing. So in other words, 12 volts minus 9 volts equals 3 volts. So we used up 9 volts there. We got 3 volts left on that branch. And so 3 plus 9 equals 12. Okay, so we've calculated our voltage drops, and now we're going to calculate the branch currents. And remember here, it's the important statement there, the sizes of the branch resistors will determine the amount of current flowing in each leg of the branch. Okay, so with all these three being equal, we're going to have the same amount of current flowing through each branch, and those added together, and that's Kirchhoff's law too, all those three added together will equal the series or the total current. So we could, from that right now, we could really deduce, we could divide 90 milliamps by 3 and get the answer, but we're going to show you the long way around because not all circuits are going to be presented to you this way with all equal values in it. So again, we use Ohm's law, and we have 3 resistors, R2, R3, and R4. And the current through R2 would be 3 volts divided by 100 ohms. So 0.0 equals 0.03 amps or 30 milliamps. Okay, so remember Ohm's law, 3 volts divided by 100 ohms equals 0.03 or 30 milliamps. So it's going to be the same for each resistor, and if we add all those together, we get 90 milliamps. So, step 1, we determine the component relationships. R1 is in series with the parallel branch of R2, R3, and R4. We calculated the total resistance at 133.33 ohms. And we calculated the total current at 90 milliamps. And we calculated the voltage drops. The voltage at R1 was 9 volts. The voltage at R2, R3, and R4 is 3 volts. Remember, the voltage across the parallel branch is equal to all the loads in that branch, or across all the loads in that branch. And then we calculated the individual branch currents at IR1 is 30 milliamps, 2's 30 milliamps, and 3's 30 milliamps. So I'm going to show you a way to prove that all this was right with, we're going to go over here to a cool program that I found. It's called Circuit Lab, and you can download this. You don't really download it, you just create an account and then you can log into it. And so it's welcome to Circuits Lab. Okay, so very cool program, and you also have a, let's see here, you get a book here. Let's look at that, and you get this book, The Ultimate Electronics Practical Circuit Design and Analysis. So it's a free book, and you got all kinds of stuff there. I've just been through parts of it. I haven't, looks like they're developing some of it. There's some more higher end stuff, but pretty good here. This would take you pretty far in a lot of electronics classes. So here's our circuit, and the simulator's all set up, and I wanted to show you how we can verify our answers here. And let me see here if I can do this so we can kind of see, maybe. That may not work too well. I was wanting to leave it exposed. I could do something fancy here with the editing, but I think I'll just leave it like this. Okay, there, and now we can see stuff. I'll close all this other stuff up here, make it a little more compatible. Okay, so if I go, we can see our value. I can slide this over, we can see our value. So we said we really can't measure resistance on this yet. I haven't figured out how to do that yet. But we can measure total current, and we can measure the voltages, and it will show us the also the power, the watts in the circuit. So everything is measured in reference to ground. So if I hold up, put my cursor over the line there, it says 0 volts, because that'd be like putting both leads of the multimeter right here on the same point on this wire, so we wouldn't measure any difference. So if we go up here, now we're measuring across the power supply, and we have 12 volts. Now we're going to measure across our resistor. So if I go right here on the resistor, you see I've got 9 volts. Delta, that means, that's a change or a difference between there and ground. So we have 9 volts, and we have 90 milliamps flowing through that resistor. So now if I go down here to my branch node, now it shows that I have, well, let me go up one. I have 3 volts right there. That would be between that point and ground, the point where my cursor's at. And then if I go to each resistor here, I have 3 volts there, and 30 milliamps and 90 milliwatts, and same there and same there. So all of our calculations were correct, and it all worked out. So I'd encourage you to get this lab and play around with it. This simulator is pretty cool, and so far they haven't charged me any money. I'm sure there's a hook here. If you want to do more things, you have to pay for something, but it's a pretty good free program, really. So check it out. If you got any questions about any of this, let me know, and I'll be happy to answer your questions. You can always email me, or my phone number is available there. If you're working on something and get stuck and it's just driving you crazy, be sure to text me, and I'll help you out as best I can. I'm usually around and can get to the phone or the computer pretty quickly. So, hey, that's it. I'll see you Tuesday and Thursday in class. Study hard, because you're gonna have to do it. As we used to say, you're gonna have to hit the books. Now you're gonna have to hit the computer. So Everybody have a great day, rest of the weekend, and I'll see you all next week.